Hello, we are the drone team from McGill Robotics from McGill University. We are presenting our drone, Terrence, for the AUVSI SUAS competition. I will now let our core members introduce themselves.
Hey everyone, my name is Ifan Lee. I'm the co-project manager at the drone team at McGill Robotics, and it's my fifth and last year studying mechanical engineering at the University of McGill.
Hi, I'm Aldo. I'm in my last year of mechanical engineering and I'm co-PM for the drone team.
Hey, I'm Philippe. I'm the software lead for the drone team. I'm a computer engineer. It's nice to meet you.
Hi, I'm Emma. I'm in mechanical engineering and I'm the propulsion lead.
Hello, I'm Vladimir. I'm electrical lead and I'm an electrical engineer in my PhD.
My name is Alistair and I'm the payload lead.
Hi, my name is Aiden, a fourth-year software engineering student at McGill, and I am the software lead for the McGill drone team.
So, in terms of the requirement and acceptance criteria, the competition this year is divided into two parts: an initial waypoint following section of a length of up to 10 miles, followed by an object detection and airdrop section. Given that the maximum flight time is 30 minutes, the UAV will have to adapt to the flight waypoint length. If the length is below 5 miles, then the top speed of 15 knots of the drone will allow it to fly through the waypoint and have about 15 minutes in the object detection area to conduct the airdrop. If the distance increases from that, then the time in the object detection area will drop, and we will have to adjust the weight of the UAV by taking on less airdrop package as a result. As such, the design criteria our team uses was a top speed of around 15 knots, as we are using a quadcopter this year instead of fixed wing, and with a flight time estimate of 30 minutes. So, let's talk about the design. Before we start, I would like to preface this by saying that the team had faced several organizational constraints this year, including limited instructional knowledge, limited time, and limited manpower. A lot of that had been lost during the COVID years, and the limited ambitions in terms of design for this year. The design of this drone has also been developed in a budget of 7,000 Canadian dollars, which required the team to use open source software and carefully allocate resources. The final design chosen was to be a quadcopter, and we were divided into multiple different systems, such as the frame, the electronics, the propulsion, the software, and the payload. The frame was to be custom designed using carbon fiber and assembled and manufactured by ourselves, while the electronic section was mostly purchased off the shelves, such as the CU-AV7 Autopilot, Raspberry Pi Model 3B+, and software handled the communication between these electronics as well as computer vision. More detail with these will be presented in the following video.
For our imaging system, we will be using the Point Grey Flea 3 camera with 1.3 megapixels, running at 60 frames per second. This camera is coupled with a 75mm lens that is used to compensate for the height the drone will be flying at. The camera will be connected to the onboard computer, running a state-of-the-art convolutional neural network, YOLO, You Only Look Once, which has been trained on the dataset that has been computer-generated by the team. Some examples of the dataset are shown.
So, for our communications, we are using three ways to communicate with our drone. First, it's RC. So we are using FrSky QX7 as our main transmitter and XR8 Plus receiver as our receiver on the drone. So it's definitely for low range stuff, and we are using two telemetries. One is Wi-Fi telemetry that is also for short distances, and the other is 915 MHz SIG radio telemetry that we are using for long range communications.
18 kilograms of thrust. With the drone weighing close to 7 kilograms, this ensures almost a 2-to-1 thrust-to-weight ratio. The system is powered by 6S100C LiPo batteries with a capacity of 12,000 mAh.
This model contains a 32-bit 480 MHz ARM Cortex-M7 core processor with a single megabyte of RAM. It runs the PX4 firmware, which is an associated flight review system that the team used to visualize flight test results. To integrate with the software, we use the middleware called XRCE-DDS. It allows us to communicate with the PX4 as if it was a regular ROS2 node in our system. This communication happens over ROS topics, which implement a subset of the Mavlink protocol. However, we decided to add an extra layer between the autopilot and the flight computer, which acts as an interface between both. It allows us to communicate over ROS actions instead of topics, as it is better practice and more maintainable.
Pilots as on flying a quadcopter and testing any new development we wanted to bring to our main drone, Terrence, beforehand. As this is the first quadcopter our team will be building, we all lacked the necessary knowledge on how to build these elements on a quadcopter. Another step we took to ensure safety was to build a gazebo simulation, which we spent considerable effort on to develop as a reliable simulation environment for missions and allowing for tests in an isolated control and risk-free environment prior to development on Little Terry. The gazebo simulator was chosen for its seamless integration with ROS, and its functionality was then extended with several custom plugins.